Hi. Hi, hi. Hello.
All right, we did it. So we continue with the last day, with the last talk of the day. We have Pedro, who's going to talk about bootstrapping line defects. Thank you.
Okay, thanks to the organizers for the invitation. Today I'm going to talk about bootstrapping line defects with auto-symmetry, which is work that we did recently with Edo Lauria, Alex Jimenez Grau, and Filine van Vliet. And we're going to consider extended objects or defects in, I don't like seeing myself, but I'm gonna. So we're going to consider extended objects or defects in conformal field theory. In quantum field theory, they are important observables. In condensed matter, they describe impurities. In gauge theories, we have the Wilson loop, which is a famous observable that tells us whether a theory has confinement or not. And for us bootstrappers, whenever you add a defect into the game, you basically enlarge the number of observables. So there are a lot of new things that you can calculate whenever you add an extended object. And of particular interest for this talk is the fact that we're going to study one-dimensional defects, so one-dimensional line defects. And this is nice because one DCFT, they are always a bit funny, right? Say, for example, a one DCFT does not have a conserved stress tensor just because in 1D, a 1 times 1 matrix, you cannot make it traceless without making it trivial. But you know defects, because they exchange energy with the bulks, they are also not expected to have a local conserved stress tensor. So if you were always a bit, I don't know, uncomfortable that 1D CFTs do not have a stress tensor, they have actually a very clean and very clear interpretation in terms of line defects. And so the plan of the talk is basically to follow the modern numerical bootstrap philosophy, that we are going to start always like from the very general, very agnostic, and then as the talk progresses, we're going to become a bit more specific, and we're going to focus on specific models. So having said that you know, we're going to start from the very general, and then we're going to focus on the more specific. Let's start discussing some of the generalities of the setup that we're going to consider. We're going to consider line defects in 3D CFTs. And because you're adding this like big object to your configuration, you're of course breaking some of the symmetry. So if the original group that you have, this 3-dimensional conformal group, was SO4,1, you will break some of it when you put your defect. And just from the picture, it's very easy to see what is going to be the remnant symmetry. So you know, in directions parallel to the defect, nothing happens. So you expect that to be a symmetry of your configuration. So the 1D conformal group will be preserved, and it's indeed the symmetry on the line that we're going to consider. But you can also have rotations around the defect. You know, this is generic when you have defect CFT, that there is this extra rotational symmetry. And so you can think of these rotations, you can think of it as a sort of spin quantum number. And we actually call it transverse spin, that it's always present when you have extended objects or defects. And then, as I said at the beginning, there are a lot of fun things that you can do, right? You can put operators in the bulk. You can put operators on the defect. So for example, you can study correlation functions of bulk operators in the presence of a defect, but you can also concentrate on excitations on the defect itself. And you can also consider more exotic things, for example, in which you have a bunch of operators in the bulk and a bunch of operators on the defect. For this talk, for the talk today, we're only going to consider excitations on the defect. Okay, so today we're just going to do one DCFT, and so we usually put a hat when we have operators constrained to the defect, but because in this talk everything is going to be on the defect, we're just going to get rid of the hats. So continuing with the generalities, as I just said, there is no conserved stress tensor when you are living on a defect. The closest that you have is what we call the displacement operator. So because you added this big object to your configuration, space-time symmetry is no longer conserved. You know, space-time, you don't have space-time symmetry, and you can think of the displacement operator as a sort of an anomalous contribution to the word identity associated to the stress tensor. And it is very general. It is an operator that you will always see on a defect CFT. Because it is related to the stress tensor, it has actually a protected conformal dimension, which in this case is fixed to 2. And it also sort of points away from the defect. So it is actually a vector on this neo-quantum number that I just introduced, this transverse spin variable. So there is no stress tensor when you do defect CFT, but there will always be the displacement operator. So this is the closest that we have to a stress tensor. The other operator that I want to introduce is also quite generic. And this one appears whenever you break a flavor symmetry. So imagine that you have a bulk CFT with some ON flavor symmetry, and then you introduce a defect that breaks this ON to an ON minus 1 symmetry. So similarly to the introduction of the displacement operator, there will be a sort of anomalous word identity associated to the flavor current. And now you can define this operator, which we call the tilt. So the tilt is basically the corresponding of the displacement operator, but now the symmetry that you're breaking is the flavor symmetry of your model. Again, because it's related to the flavor current, it has a protected conformal dimension, which in this case is delta equals 1. And it is actually, for this particular symmetry breaking pattern that I'm considering, it is actually a vector on the remnant ON minus 1 symmetry. And again, the displacement is quite general, quite canonic. It will always be there. This one needs a flavor symmetry, but you know, flavor symmetries are also quite a generic phenomenon. So the tilt, it's not as universal as the displacement operator, but it's still an operator that you expect to see a lot of the time. Yeah, of course. And you can also consider, for example, different sorts of symmetry breaking, right? You could consider some OM theory that it's breaking to some ON. So you can do, you can have a lot of tilts, or you can have like 0 tilt. So that's an important thing. For this talk, I'm going to focus on this particular symmetry breaking pattern. You know, I'm going to go, and actually, we're going to be even more specific because the title says O2. So actually, in this talk, we're only going to consider O3 to O2. But in principle, you could consider more generic things. In particular, not even breaking the flavor symmetry, as you just pointed out. You mean a defect that preserves the conformal symmetry? Yeah. Yeah, that I'm not going to consider in this talk. In this talk, we will always break it to this subgroup. So then the techniques that we're going to use is the modern numerical bootstrap, and in 1D things are a bit different. So first, the operators, you have to consider them order on the line. You know, there's not much space on a one-dimensional line, and so it's nice to think of it as really as a circle, and they have this cyclic symmetry. You can write the famous crossing equation that you obtain, you know, by taking OPE pairwise. And one main difference with the standard crossing in higher dimension is that in 1 dimensions, you know, there is again less space, less coordinates. So in this case, there is only 1 cross ratio. So instead of the usual U and V cross ratios that you see when you write crossing symmetry, in 1 dimensions, you only have 1 cross ratio. Again, because there's not much space in 1D, you also do not have a spin variable. However, there is there is an analogous discrete quantum number which we call parity, and this parity is associated to reflections of the line in which your defect sits. And you know, you can order your operators whether they have positive parity or negative parity. So there is no spin in 1 dimensions. But this parity sort of plays a role of the spin, in the sense that, you know, you can classify in higher D, you can consider operators with even spin and operators without spin. In this case, you can consider operators with even parity and without parity. And again, this study there are a lot of experts in the audience. Of course, this is the starting point of the bootstrap, but even in 1D, even with only one cross ratio, solving this equation analytically and in full generalities it's a complicated task. So we rely on numerics. Now, again, I know that there are a lot of experts in the audience, but as far as I understand, there's also people that perhaps are not that familiar with the numerical bootstrap. And sadly, I do not have the time. Also, I am not one of the masters, so I will not explain to you how the techniques that we use to study this equation numerically. Let me just tell you that the idea is to put exclusion bounds, numerical bounds, on the dynamical data that appears in this equation, which is basically these coefficients, which are 3-point function coefficients on the 1D CFT and the spectrum, the conformal dimensions. And as I said, the techniques I'm not going to describe, but if you're not a numerical bootstrap expert, I'm going to show you the plots, and hopefully the plots will be self-explanatory. So if you're not familiar with the bootstrap, at least when you see the plot, you're going to say, okay, that's the type of plot that you can get. So then, as I said, from the very general to the specific, let's start with the 4-point function of one of these canonical operators, the tilt. So this is just a standard 4-point function in CFT. We have two OPE channels. We have this tilt is an O2 vector in the configuration that we'll consider. So I'm going to use this sort of complex notation of T and T bar. On the TT bar channel, we have the identity, and then we have two low-lying operators that can have parity odd and even. And in the TT channel, we have a guy with parity even, which I call T square. And again, you can compare it with the analogy that I made with spin, right? If I have a complex scalar in a higher dimensional CFT, in the 5-5 bar channel, you can see even and odd spins, while in the 5-5 channel, you can only see even spins. And then, now that the system is there, crossing is there, the numerical algorithms are there, we can start cranking the machine and producing bounds. And as I said, if you're not familiar, perhaps...
Pedro?
Yes.
So this correlation function, they do not satisfy any additional constraint? I mean, how do you distinguish from a generic scalar? Well, from a generic operator in one.
Yeah. As I said, from the generic to the specific. So as the talk progresses, I'm going to start giving info to this crossing such that we steer it in the direction that we want. But for the moment, I'm being very general. Indeed, actually your comment is very important, because this is an SO2 1D correlator, because the tilt transform in the SO2 of the flavor group. We can write a similar equation for the displacement operator, but the displacement operator transforms in another SO2, in the SO2 of the transfer rotation. But of course, the bootstrap cannot distinguish between those two. So if you just study the single correlator tilt and the single correlator displacement, it's the same code basically. The bootstrap doesn't know that you're doing flavor. So it's important indeed that as of now, we're actually not giving much information. And indeed, as you just were asking, then the theories that you were asking, where are they? Well, they're actually there in the plot. So then the idea is the following: we put upper bounds, right, on the operators, on the conformal dimensions of the operators that appear in these channels. And again, if you're not familiar with the bootstrap, the idea is that there is here an operator which has dimension delta, some value, and then in the numerics we assume, right, that a continuum of operators. So we choose a minimum value for the first guy that appears, and then we allow every value that comes afterwards. And so then you can start playing games and pushing this gap. So you can assume that there is an operator starting at 1 and up, or at 1.5 and up, and 2 and up, and then that's how you impose your constraints, right? So this is the type of game. And at some point, these gaps are perhaps too extreme, and then the numerics tell you that's inconsistent. So that's the bound games that we play. So this is basically an upper bound on the TT bar guy with odd parity. So one of the guys that appeared here, versus the gap, the conformal dimension of the lowest lying guy appear on the T square. And so this is the bound that we get, and the color coding, the color grading comes because we have also, we have this parity odd and parity even. So there is another operator here with its own independent channel, and we can also play with that one. So the color grading is precisely that. Seeing that we can also start putting gaps and playing with the conformal dimension of the TT plus, we did it. And so the lighter color basically means no assumptions in the TT bar plus. So we leave it as it is. The unitarity bound tells us that operators with dimension 0 and up are allowed. And so in that channel, we allow operators with dimension 0 and up. And then the darker the color, we start, increasing that gap. So it's a 2D plot, but there is this sort of hidden third variable, which is the gap of this extra channel. And the more we push the gap, right, the darker the color, the bounds tend to get stronger. So then this is very nice. And then, as a check, and in order to see where your theory sits, we've added these dots. These dots are known solution to crossing symmetries. So these are solutions that your numerics, in principle, should not rule out, right? Because if you are doing everything consistent and you have a solution to crossing, the numerics should give you an allowed region, and whatever known solution that you have should be in this allowed region. And so as a consistency check, we see that it works beautifully. One is the generalized free boson in 1D. The other one is the generalized fermion in 1D. And that yellow dot is actually fun, because this is one of these, it's an epsilon expansion resolved for an interacting model, which is one of these specific models that we're going to study later, the ones that I'm going to introduce later in the talk. So then this is one of these very generic, very agnostic plots when we make really minimal assumptions. And as I said, I presented the tilt. For the displacement correlator, you can do a similar plot, and that one is in the paper. So the other fun thing that one can do, and now here you can start distinguishing between these two SO2 symmetries that you have, is to consider a mixed system of operators in which you consider now the two canonical ones, right? The two operators that we know are almost always there, which is the displacement and the tilt. And the nice thing of considering a mixed correlator is that it gives you access now to new data that you didn't have before, right? The tilt correlation function gives you access to some operators. The displacement correlation function gives you access to other operators. When you consider the mix, now you have this TD channel that you didn't have before. And then we play a similar game, like again being very agnostic. And now it's a 3D plot. It's harder to see, but we put a gap on the dimension of the operator O plus, which is the common operator that appears in the TT bar and DD bar OPE. So these guys have basically the same quantum numbers for parity even. And then we again play with the gaps that we have in the other channels. And in particular, we're using as an access the new operators that we didn't have before. And the dots again are these known solutions to crossing. So again, this plot actually is admittedly not that exciting, in part because we're being very agnostic. But let me assure you that the known solutions are actually comfortably inside the allowed region. And then precisely because we are doing this agnostic approach, these plots should be valid always. So if any of you are 1D experts and you have a bunch of theories, perhaps coming from condensed matter system that you're familiar with and data, you should put them in this plot, and they should be in the allowed region. So then that was like sort of the warm-up, the sort of generic bounds that we can get in this system. But now then let's change gears and let's try to start giving a bit more information in order to focus on some models of interest. And the first model of interest is what we call a monodromy defect. So a monodromy defect, consider a bulk theory with an O2 symmetry, so with two scalars, such that you can use complex notation and define a complex scalar in the bulk. And imagine that when you rotate around this line, your scalar acquires a phase. So this is what we call a monodromy defect. And the nice thing is that this system actually has been studied quite recently in the literature, and so there is actually some data that we can actually use and then plug into the numerics. And so some of the data that it's available is consider your bulk field, even though I told you that we're going to focus mostly on the line, but consider your bulk field and then move it closer to your line. So this limit, it's what we call the bulk to defect OPE limit. And basically your bulk scalar, this complex scalar phi, when it goes closer to the line, you can think of it as an infinite sum of defect excitations. So now it's the sort of the defect analog of the OPE. When you fuse two operators in the bulk, you can write them as an infinite sum of bulk operators, local operators. When you move an operator to the defect, you can write it as an infinite sum of defect operators. And these modes, which I'm calling psi, are basically the defect modes of this file phi. And first, because of this monodromy, they actually have a fractional transfer spin. So these are the allowed values that this phase gives you. So it forces you to have these fractional values of this spin variable. And then their conformal dimensions are actually known. They have been calculated in the epsilon expansion up to order epsilon, which means that then that this is data that one can give to the numerics now in order to try to steer them in the right direction. So also from the epsilon expansion, we can look at the OPE, and for example, in the OPE of psi and psi bar, remember that these are the defect modes of this bulk field. The first operator that appears is the displacement. Right? Remember that the displacement has protected dimension 2. So in principle, there could be operators before the displacement, but when you do the epsilon expansion analysis, it seems that the displacement is the first one that appears. So we're going to use that as an assumption. So now we want to do the numerics in 3D, and we are going to make this gap assumption. We're going to make the assumption that there are really no operators before the displacement on this channel. It's not a rigorous proof, but you know, sometimes we like to trust the epsilon expansion, and in this case, we're going to use it as an input. And the other input that we're going to give is also the conformal dimension of the external operators, right? So these values that come from the epsilon expansion. So with that input, then we start cranking the numerical machine, and now we're going to find an exclusion curve for a conformal dimension, but as a function of a 3-point function. So this is the first 3-point function that appears in the talk. I told you that with the numerical bootstrap, you can put bounds on the conformal dimension and also on the 3-point couplings. And so then this, I don't know, in this plot, you can see the glass half full or the glass half empty. So on the one hand, sorry, there is actually an important point that I forgot to say. So let me go back a bit. Again, the numerical bootstrap experts know that when you're doing the numerics, you usually want the theory that you're looking to be as close to the numerical bound as possible, right? There are technical reasons, because then there are actually techniques in when one can extract actually a lot more data, basically the spectrum of the theory numerically. And again, if you're not a numerical bootstrap person, it is just intuition, right? In any branch of physics or mathematics, whenever you have a bound, you usually want your bound to be as optimal as possible. So having said that, and going back to the plot that I was looking, this red dot is the generalized free theory solution, and this black dot is the order epsilon correction. So as you can see, yeah, it's either the here it is. You know, it labels both the conformal dimension and the spin, and you know, for us that's actually an important point. For us, it's a free value in the sense that you can study all sorts of monodromies. Actually, for that plot, I chose one particular value, which is 1/3, which is actually, there is a reason for that, but perhaps I can tell you later. But for us, in principle, you can choose any value of V that you want, but it basically labels your monodromy. And okay, going back to this plot is that, you know, the black dot is the interacting theory coming from the epsilon expansion, and it's not that close to the numerical bound, at least not as close as we would like to. Here I should point out also that the color grading is a bit different. Now light green and dark green basically means numerical precision. So this lambda describes you know, the number of derivatives that you use to approximate your crossing symmetry in a Taylor expansion. So basically, the bigger the lambda, the better the numerics. So lambda equals 33 is the best that we have so far. And again, the interacting theory is kind of deep inside the bound, but I think it is a good sign, and that's why I say perhaps glass half full is that, you know, the epsilon expansion, the correction moves it up, right? So it moves it closer to the bound and not down. Down would have been terrible, but it moves it up. And you know, with improved numerics, the bound should keep going down. And the other thing that I would like to say is that I told you that we used input from the epsilon expansion. But actually for this model, for the monodromy defect, there is not that much data. So we gave this gap, you know, in the displacement operator. We assumed that it was the first operator that appears. We also gave the dimension of the external operators, but in principle, you know, there are more channels, there are more operators, there are more gaps that you could also input to the numerics. We don't have that data. So that's why we didn't input it. But in principle, perhaps one could calculate it, and then this plot will improve. And now why do I make that comment? And Junchen, I am, by the way, I'm not skipping your talk. So at the end, remind me of, I'm not skipping your question. At the end, remind me of the 1/3, because I really have a comment. So why do I make the comment regarding data coming from the epsilon expansion? Because the second model that we're going to study, which is called the magnetic line defect, in this one we do have a lot of data. So in this model, we're actually going to be able to give a lot more info to the numerics. And I should also say that, as I said, the logic was to go from the specific, from the very general to the more specific. But in a sense, this model, and in particular the paper by these people, was what motivated us to study this system. And the reason is that this line defect seems to be a very interesting model that seems to be related with a lot of actual condensed matter system that one can measure, you know, in experiment, that one can see in the laboratory. And in this paper, they studied this model analytically using epsilon expansion and large N techniques. And so a natural question was whether the numerical bootstrap can actually find this very interesting. So it is a 1D line defect with O2 symmetry. And so in principle, it satisfies all the constraints that we are putting into our crossing equation. So in a sense, this was our motivation, and I want to show you the results that we got.
Peter was the first one who studied a related model, actually.
Okay, good. Yeah, sadly, I am not an expert with the actual, you know, condensed matter literature, and I must confess that when I was reading the Cuomo et al. Paper, you know, that there are all these beautiful condensed matter theory papers that just by reading at the title, I could have never realized that they were line defects, but they are. You look at the title and they talk about fermions, localized fermions, etc. And what is that? But they're actually line defects. Okay, so having said that, then let's review this very nice model. And well, the great thing about this model is that it has a Lagrangian formulation. So you know it cannot be more explicit than that. So you have a bulk, you know, a Wilson-Fisher theory in the bulk, and then you define this following line defect, which is sort of reminiscent to actually a Wilson loop, a Wilson line. Of course, there are no gauge fields here, but you know, it's kind of like a scalar version, is an exponential of one of your fields. And as you can see, this one breaks we're going to consider an O3 symmetry in the bulk, and this one picks one direction, in flavor space, so it breaks the symmetry explicitly from O3 to O2. And so it will have a tilt, so it will have one of our favorite operators. And this phi1 now, you can think of it as the spin variable. So I'm going to call it the spin variable. It lives now on our 1D line. These people calculated, did a order epsilon, a second order, a two-loop calculation in the epsilon expansion in order to extract data. And then they use some pair summations in order to improve the result. So there is an estimate for the conformal dimension of this guy, which I'm going to call the spin variable, and it's 155. And again, because it is actually a Lagrangian description, we can identify all our main characters. The displacement operator is actually given by delta nabla phi, where this nabla is actually a transverse derivative. And this is basically the only candidate, right? Because we know that the conformal dimension has to have delta equals to 2. So it has the correct conformal dimension, and because this nabla is actually a transfer derivative, it also has the correct quantum numbers under SO2. And it's not that just that it is the natural candidate, but as far as I understand, they also calculated corrections to the conformal dimension of these guys, and it turned out to be protected at one loop. So then this is the model, and so we're going to study then the mixed correlator bootstrap system that we're going to consider is the tilt and this spin variable. So a couple of comments are in order. First is that, one of the nice things that it has is that one of the external operators appear itself in the OPE. And this is reminiscent of the Ising model island in the mixed correlator. That the spin field can appear in one of the OPs, and that seemed to put very strong constraints on the numerics, and indeed that's how you get this high precision island in the 3D Ising model. And the other thing is that now we have all these operators. I mean, they have these funny names, but they're not that important. So the first guy that appears here, I'm going to call A. The first guy here, we're going to call T. The guy that appears here, we're going to call V. And the nice thing, unlike the monodromy defect, is that now all these guys were actually calculated by Cuomo et al. So we have epsilon expansion estimates for these conformal dimensions, and that's how we're going to help the numerics. And here I would like to make a comment is that, we want to focus on this magnetic line, but without help, I mean, there's very little we can do, right? There is all this combination of operators, right? I mean, doing a 4-dimensional scan, varying every single conformal dimension is just not feasible. So using the epsilon expansion, it helps us to go in some direction. But I would like to, in case someone complains, is that the epsilon expansion, it is a rough estimate. And that's an important comment that I want to make, because it actually might have relevance later when we interpret our results. So the point is that we need a starting point. The best starting point that we have at the moment is the one loop epsilon expansion. And the logic would be the following. So we start with this rough starting point, we crank the numerical machine, we see what we get. And if we get something interesting, perhaps we then can go back and improve the original assumption in order to get even better results. So that would be the idea. So having said that, we will just boldly put epsilon1 in all these epsilon expansion results and just feed it to the numerics. And again, inspired by the Ising model island, we're gonna plot, an allowed region between these two external operators that we have. So there is no island here, but there is some good stuff. So for example, the tilt is protected, as I've been saying in the talk. But in this plot, we decided to keep it arbitrary. So we wanted to see, how the numerics do. We're going to help the numerics, and we're going to explore now the allowed region for the spin variable, which there is an estimate from the Cuomo et al. Paper, and the tilt operator. And you see that the tilt, the allowed region, there is a lower bound, which is already above 0.9. So that's quite good. It seems that the numeric is rediscovering the tilt and telling us that this operator, it should be there. On the other hand, the lower bound on the spin variable is around 0.6. And remember that the estimate is 1.55. So this one is actually quite weak. So then let's keep pushing, right? We're gonna, seeing that the numerics is rediscovering the tilt and you know the bound on the delta phi is not that great, we're now gonna input the tilt, you know, in addition to the gaps that we already had. And now we're gonna scan for allowed values for OPE coefficients as a function of delta phi. So now I'm gonna include the tilt and I'm gonna scan an allowed region for OPE coefficients as a function of delta phi. And the hope is that, you know, if there is some particular value for delta phi in which you see a feature, then that might be an indication that there is a theory living there. So then it's really a 3D plot. It's the allowed region for these two OPE coefficients as a function of delta phi. So I'm going to show you a slice of this 3D plot. And this is what we find. So this is same color grading as before. Light green means good numerics. Dark greens means even better numerics. and as you see, you know, there is this intriguing cusp, right? That the numeric doesn't want to disappear. So the question is, why is this cap there? And it seems that with better numerics, it seems that it's getting even sharper. Is there a theory living there or not? And more importantly, is the magnetic line defect that we were looking for? And so one important thing is that I told you it's a 3D plot and we're taking a slice, but we're taking a slice for actually a very low value of delta phi, which is 1.2. So we seem to find a feature in our numerical plots, but the feature sadly is not really where we want it to be. And so then, seeing that we actually have the estimate of 155, why don't we now go and see the same plot, you know, at 155, and then this is what we get. So you see the feature is gone. That black dot is the estimate, is an estimate coming from the epsilon expansion. It seems that we're ruling it out, but not really, because actually the assumptions that went to the numerical plot are not quite the same as the assumptions that went to calculating this dot, but at least, you know, everything seems to be pseudo consistent with each other. And you know, there's no feature here. So and then I don't know. I actually want to invite the audience to sort of interpret this thing together. So I'm gonna tell you one of the interpretations that we have. So one possibility, which is what I call the sort of the wishful thinking possibility, is that perhaps this feature it's here, but we're just missing it because of numerical precision, right? So if we could crank the numerics, you know, to higher and higher values of derivatives, you know, perhaps, you know, these bounds will start coming down here, right? And then the plot at around 1.5 will look a bit more like the one around 1.2. So that could be one thing that could help us help with our quest. A second thing is that recall that the original approximation, so this one loop gaps are a rough approximation. So perhaps, you know, with a two loop with a higher order epsilon expansion calculation, you know, some of the gaps are going to go down, perhaps some of the other gaps are going to go up. So perhaps, you know, with an improved starting point, it could also be, you know, that this feature starts appearing around 155.
Sorry, Pedro. Here you are injecting the dimension of the other operator from epsilon expansion, or you're leaving them?
The gaps. I mean, the gaps. But now I'm keeping the spin as a free guy, right? That's a free guy, and the hope is that, you know, hopefully the numerics is going to signal. So again, to tell you that the dreams that were not true, right? If we had gotten this feature for 1555, it would have been, we would be jumping up and down, but sadly it didn't happen. And so the other thing that I want to say is that, you know, the 155, it comes with an error bar. And you know, we want it to be as low as possible. So it could be that perhaps, you know, with improved epsilon expansion and input by the approximation that 155, perhaps it goes down to 1.5, perhaps even to 1.4, that will help us even more. But that's why, you know, I call this the wishful thinking. So the question is, does this feature describe the magnetic line defect, yes or no? A lot of things have to happen. You know, a lot of moving parts have to fall into place in order for this thing, for both results, you know, to be consistent with each other. But it is a logical possibility. The second option is that perhaps this is some other model, and again, going back to our original assumption, it is a rough estimate, right? So it could be that more than one model is consistent with those gaps. And so if that's the case, you know, perhaps this is some other theory, and that's why I asked the expert of audience, you know, if you're aware of a 1D theory with a spin field with dimension around 1.2, you know, let us know, because perhaps we discovered your model by accident. So that's the state of things. I would call them intriguing. So let me then just conclude. So we started with we implemented this numerical bootstrap for line defects with autosymmetry. We started from the very general to the very specific. We put as much information as we had coming from the epsilon expansion in order to focus on these two particular models, the monodromy and the magnetic line defect. And I think the results, especially that we got from the magnetic line defect, are intriguing, but not fully conclusive. For the future, of course, people in the audience already asked questions. You could consider, for example, more general patterns of symmetry breaking, more general ON symmetries. One thing that I like a lot, because it's close to my heart, seeing that a lot of my research involves superconformal theory, is that you can actually repeat this analysis with superconformal models. So if you have a bulk theory, you know, superconformal models usually come with a flavor symmetry for free, which is the R symmetry. So if you have a bulk model that has enough supersymmetry, whenever you put this line defect there, you will of course break some of that symmetry. But in some situations, you know, there can still be a remnant. You know, you can still define a defect that is half BPS. And then it's really nice because you have a defect that has supersymmetry, and for example, you still have some R symmetry that you can use to define monodromy defects. And indeed, we've been exploring this thing, and for example, the displacement operator, which is protected, then it will sit in this superconformal version in some particular protected multiplet. The tilt operator, which is also protected, it will sit in some protected multiplet. So then you can go calculate superconformal blocks, you know, implement the numerical machinery, and start cranking, start using the numerical bootstrap again. And one of the motivation is that, you know, looking for data. We know that sometimes when you have supersymmetry, some exact results are possible. So when you have a defect in a supersymmetric model, perhaps you can do some exact calculations thanks to supersymmetry that then you can fit to the numerics. So as I said, this is work in progress. And finally, to answer Junchen with your V over 1/3. So one particular supersymmetric model that you can consider is the West-Sumino model that has like a 5-cube interaction, right? Superpotential. And V equals 1/3, it is actually the only value consistent with that Lagrangian. So for our analysis that was bosonic, this monodromy guy was a free parameter, but it could be that for 1/3, we're actually studying monodromy defects in some bulk supersymmetric theory, but a monodromy defect that is not preserving any supersymmetry because we didn't put any SUSY in our input. But it could be that there are just monodromy defects that break completely the original supersymmetry. So I think the value v equals 1/3 might be relevant for SUSY. Okay, thank you very much.
Questions?
So is there any chance that the feature you see might be the supersymmetric model or not?
Well, this was for the magnetic line defect. So question, can you supersymmetrize that beautiful Lagrangian construction?
No, I mean some other Lagrangian somehow.
Yeah, of course. It could be anything. In particular, supersymmetry, even though we didn't add it, but
with supersymmetry, the tilt operator, right, or no?
Give the
in
same
multiplet. Sorry.
I'm not so sure. I think it depends. I think I don't remember. We discussed this with my collaborators. I think they are different. But what's interesting is that because you have supercharges now, there are also sort of tilt associated to the supercharges, right? So you also break half of the SUSY. There is an anomalous word identity, so you have now operators that you can associate with the breaking of supersymmetry. And I think, again, this is sort of work in progress, but I think the way it works is that, the tilt sit at the top of some supersymmetric multiplet, and the displacement that has dimension 2 sit at the bottom of a supersymmetric multiplet. And the highest weight is like one of these sort of supersymmetric tilts, like associated to the breaking of supersymmetry, and the other one, so somehow the current, right? I'm confusing myself. So it seems that there will be two tilts associated to supersymmetry, and one of them goes to the multiplet where the displacement operator sits, and the other one goes to the displacement where the tilt sits. But I don't think that the tilt and the displacement are in the same multiplet.
Because I was just thinking in the bulk, the R current and the stress tensor are in the same multiplet. So
yeah, sorry. But for example, in N equals 4 super Young-Mills, you're right. When you put a line defect in N equals 4 super, and that's because the group is gigantic. So the multiplets are very big. So indeed, in N equals 4 super Young-Mills, the multiplet looks something like this. And indeed, the displacement is actually a super conformal descendant. But I think in that case, it's because you have a lot of symmetry. In this example that I showed, I don't think there's enough symmetry for the tilt and the displacement to be in the same multiplet.
Any other question?
I guess I don't think so. And indeed, what you're pointing out, maybe one of the flaws of just concentrating on one of the things, right? Perhaps a proper analysis, should include a combination. Yeah, I don't know. As I said, sadly, when you focus on the defect, you're actually pretty ignorant regarding bulk data coming from the bulk. Some things you can input, but you really miss a lot of information from the bulk. So that's what I was saying, that perhaps in the future, we should really consider more ambitious configurations in which you put a bunch of bulk operators together with a bunch of defect operators, so that you can really tell your defect, hey, this is the bulk in which you live in.
Okay, let's thank Pedro again.